Okay, there we go. All right, starting again. So we're going to start by reviewing some of the things said last week. And I think the biggest change is that I'm going to try to emulate real-time sort of a blackboard writing type experience, at least for myself, because I find that to be more stimulating. Hopefully this will be helpful to you. Obviously, these notes will be shared. And there's an, it would also potentially help, since I now have two screens, it would help if more of you keep your videos on. That way I can sort of gauge understanding. I will think of ways of incentivizing you guys to keep more your video on. I know a lot of instructors that do well in that regard. I haven't cared, but except now I'm realizing it actually does matter to me. Okay, anyway, without further ado, we'll start by reviewing what we mean by complexity. So usually we think of a computation that involves a number, an input, which has n bits. You might, to learn something about a function or to compute something, you might need a large number of operations. These are the difficult computations that we're typically interested in, and so things difficult are things exponential in n, and the simplest one is basically just asking of the space of all possible inputs. For example, if you have a function, you want to know if that function is even on some space or odd, you might have to check every single point, every single call to the function. And that's a lot of calls. That's 2 to the n calls, okay? So these are the difficult problems that we try to tackle with quantum algorithms, because the easy problems are easy to tackle. Now, one side issue of complexity is that, so there's a function f, which we usually treat as a black box. It's called an oracle machine, because it's a black box. You just ask it, assumed to be cheap, and so in that sense we just count the number of times we call the oracle. However, in real world implementations may be difficult. Okay, we're not going to worry about that until we get to so I know that some of you who already submitted writing projects are going to talk about real qubits, so we might hear some real world implementations of sort of oracles. So another two pieces of review is that there are two building blocks of the Deutsch algorithm, and the other two algorithms that I think I wanted to cover last week. I think I covered Bernstein-Barzirani, and I started Simon but didn't. Which both of them are, so you can see that I wrote here that I consider those as derivatives of Deutsch, because once you understand Deutsch, it's kind of obvious how to apply it. So the two building blocks of the Deutsch algorithm are the Hadamard transform and the phase kickback. Okay, so in the interest of making things slightly more interactive, let me see if I can find the way to polls. There we go. So I want, since I spent, okay, there we go, launch polling. So the question is whether all of you understand Hadamard transform. That'll determine how much I talk about it. So I'll start writing anyway. But let's see what, so people mostly understand it. I'll go fast. Okay, sounds like I should go. should spend some time on it. Okay, that's fine. That's good, in fact. Wait a second, I just lost my notes. There we go. So for a single qubit, the Hadamard transform is a rotation basically takes the just abuse the notation a little bit, right? So the one state is rotated to a 0+1 combination. The zero state is rotated. Sorry, the zero state is rotated to a 0+1 combination. The one state is rotated to a 0 -1 combination. Okay. So this is generally useful if you want to take a task and try to do it in parallel using quantum computers, right? Because the idea is that if 0 and 1 are the two possible inputs, if we want to learn something about the function, if you want to call a function on 0 and 1 simultaneously, you have to feed to it input which is superposed, right? So it's 0+1. So that's basically the idea why this Hadamard transform is routinely the first step in the computation. You kind of want to just start with a with mixing up things thoroughly, right? So the guy that all of the standard stuff is basically here. So I'm not going to spend too much time on it. So when I write 0 to the n, it's a shorthand for saying that each register is initialized with a 0, right? So if you have n registers, can you, by chance, I should have included a poll. Can you read my handwriting? Sort of, whilst I'm talking. Okay. You have no idea. All of this time I've been trying to focus on preparing notes, like slides. And I generally, what I do is I do some handwriting and then I prepare slides, and I realize that if I just focus on writing more, it's much more engaging for me. It's so much easier to focus on the ideas rather than worrying about presentation, right? Doing PowerPoint, and PowerPoint is just stressful. Anyway, so I decided that I'm gonna, at least for now, experiment with just doing things kind of like this old-fashioned way, because it's just totally different experience. Pleasant, even. Anyway, so what's the idea? The idea is that this is what we mean when we talk about Hadamard transforms on the entire sort of an n qubit register. So we start with a bunch of stuff all in 0 state. I'm going to be very sloppy here, and then we're going to hang a Hadamard transform on each leg, right? You guys have seen this already in Qiskit. Right. So I think for the purposes of actually computing stuff, we want to have a more formal notation. So if we apply a Hadamard transform on, say, on the 0 state, we get, an object which is 1/2 n/2. It's a bunch of these square roots, and then we get this object, which again, I just want to make sure that notation is not going to trip you up. So X is a space of all bit strings, and each bit string is some combinations of 0 and 1s. Okay, and so this is a horrendous superposition of all 2 to the n bit strings, right? If you do the same, and this is basically the guts of the second algorithm that we're going to see. If you now instead of x naught, let's pull one of these bit strings and hit it with a Hadamard transform. The normalization thing, the 2n/2 is the same, but what you see is that whereas here each of these was essentially a 1, right? Because everything, if you start with all 0 state, each 0 gets rotated into 0+1, so there are no minus signs floating around. The crucial thing is that if you take some arbitrary bit string, right? 0, 1, 0, 1, 1, 0, whatever, right? That's, that's that guy. Then what you're going to find is that depending on the combination of these different phases, you're going to get some combination of -1s dangling there, okay? So you can see that this is a dummy variable, this is a dummy x, this is x naught that sits in the input, and whether or not it's -1 or +1 is determined by a dot product of x and x naught, okay, the dummy variable. And you can convince yourself, I don't know, starting with the 1 bit and 2 bits and so on and so forth, that this is really the formula, right? So these are all bit strings. Let me just, right, so this is a bit string, this is a bit string, this is a bit string, right? So in all of these sums, you're summing over all possible bit strings, okay? So this is important. So this is basically, let's say, important. Keep in mind, I will say, okay? Keep in mind. Whoops. Sorry. Okay. Now, obviously, Hn is 1, right? So you can check that. So if you think of, the fact that Hn operates one leg at a time, all you have to demonstrate is that this is, the identity, and then it follows that you can basically do this for a bunch of legs, okay? Now, if Hn is 1, you won't be surprised that, you shouldn't be surprised that Hn operating on x naught gives you back x naught, right? That seems like a triviality, but if somebody told you that you could just take a state that's written like that and you hit on it with Hn, you get back x naught, the first person to make that observation gets to put its name on it. That's the Bernstein-Bazarani. So you keep this in mind, because one of the algorithms we'll talk about is essentially just based on this silly observation, okay? I mean, I don't want to, what's the word? I don't want to diminish the significance of this. Like, it's the usual thing, right? The first time somebody does something, especially if they're computer scientists and they don't think of linear algebra the same way, if physicists think, it seems like a big sort of a deal. So anyway. All right, so these are the 2 points. So this is a review of Hadamard. Actually, you know what? I'm gonna make use of all these polls that I made, and I'll ask the poll again. Do you understand the Hadamard transform now? I don't promise to go over this again. What I'll do is I'll ask people to unmute and ask them questions, because I don't. It's such a crucial building block. I don't want to, like, no child left behind. Okay, that's my attitude towards Hadamard. All right, we're getting better numbers. I mean, don't be afraid. I mean, I don't want to discourage people from being honest. If something seems unclear, I'm very happy to. I mean, I'm very keen on making things more interactive. I think it's really important for this class to succeed. Okay, so it seems like we're good for now. So the second point of review is the so-called phase kickback. And I have to say that I wish, so we did cover it probably 3 weeks ago, because I was just kind of like following Kiskit's sort of ordering of things. And it was kind of a cute example of how things work. So you remember, so let me remind you of the level of discussion in Qiskit, which was going like, oh, look, neat trick. All right, so 5 people responded. We've got, just a second, I shouldn't be distracting myself, but I am distracting myself. There are 6 people here. 1 person did not respond. So 1 person fell asleep, hopefully not died, but definitely fell asleep. Let's see. Okay, I'm not gonna screw around with polling too much because this will crash my computer at some point. All right, let me get back to writing, which is a very stimulating activity, actually. Let me ask you, for some reason, Zoom always logs you out. Worst case. 1 second. So I want to ask the same poll whether face kickback is something you guys understand. Do you understand face kickback? Yes. Very silly, but since you guys are all hiding behind your there are better ways of doing this, I'm sure. All right, lunch poem. Okay. All right, it's basically the same breakdown as before, so I'll try to be brief. Let's see, close. Okay, so I'm not gonna separately poll whether you understand the C-naught gate. I will just write down the answers. Right, so the idea is that the gate takes 2 inputs and it flips the second bit depending on the value of the first bit. Okay, that should be okay. So there are boring outcomes. The boring outcome is this one. Right, the idea is that we're going to take this sort of a classical operations, and now we're going to do superposition, right? And because we know what we're looking for, we're gonna organize things in a certain way, right? So if the first bit is 0, it gets sent according to these rules to nothing, to itself, okay, right? This is same, boring, okay. Now, if the first bit is 1, you can see something really cool, because 1 gets sent to 0 plus minus 1, 1, right? Because if you follow these rules, what you observe is these guys get flipped. So naively, these guys get flipped. Let me keep the signs the same. And that just means that you acquired a minus sign. Okay, that makes sense? Okay. And so the consequence of this is that if you now feed to it a 0 plus 1 state, okay. So actually, wait, I made a mistake. I'm sorry. it's important that it's this state is chosen because, if you apply, in fact, since I screwed up, let me do some more writing to punish myself. Let me extend the boring category. Boredom is the punishment. Right? So the boring category is extendable by having another state which gets updated the same way. Right, so this is also boring. So these are all boring. And this is interesting, okay? So now the idea is basically that if you take a linear combination, which is 0 plus minus 1, and your target state is this anti-symmetric gun, then if you apply a C0 gate to it, it flips +1 to -1, okay? So this is how we discussed it before, and that's fine, right? There was a Q diagram, right? Basically, if you think of the way to make all of these positions, what you're trying to do is you're trying to understand how this can be made equal to that, right? The reason it's called a kickback, right? So obviously these two are not the same, okay? You just get screen and polling, okay, sorry. Not right. Obviously these two gates are not the same. One of them, to switch target and control, but what you observe is that because of this operation, right, you manage to screw around with the control bit, Q bit, right? And so that opens up a possibility, and let's see if I get it right, that if you start adding Hadamard gates here and there, okay, then this is correct, okay? So what you see is that by going in and out of this sort of a rotated basis, you can essentially reverse the action of the control knot operation. Okay. Okay. It's a trick. It's the truth, and it's the trick, and it's very counterintuitive if you're coming from sort of gate operations. What we'll actually need repeatedly is the more general sort of version of this. And so I'll refer more generally. And so you should refer back to the discussion in the book, because at least so far, I haven't found an equally clear discussion in Qiskit of this, right? So more generally is that if you now think of a oracle or function as operating on inputs, right? So we'll say that there is a register X, which could be, big, right? And there's a register Y, which is, so I'm going to try to pack as much as possible into this notation, right? So these are, right, so sorry, Z2 is basically 0 and 1, basically a single qubit. Z2, and I think that's the notation used in the book, so I'm gonna use it so you guys are comfortable with it, is basically an n qubit register, okay? So the idea is that this is the argument of the function, and this is output register, right? And so the idea is that the function operates, let me just make sure that my screen is my screen showing up? Yeah, okay, good. Okay. So I just got nervous. So the function operates, whoops, did not need to do that. Second. Okay. So the function operates by sending this to y plus f of x. Okay, I think this is just an agreement that this is what we mean by function operating. And the idea will be that this is, so far, these are bit strings, right? This is a n-bit string, and this is a 1-bit string, right? But what we're interested in is making this function operate on quantum states, quantum inputs. So the assumption, again, this is going back to designing oracles and whatnot. The assumption is that you can represent this function as a n-channel input, right? And then it'll do something here, and it'll spit out its output into this channel. So this is y, and this will be y plus f of x. And as usual, we imagine initializing all this stuff to zeros. So, because if y is initialized to 0, then out you'll get y, f of x itself. 0 plus f of x is f of x. Okay, and so this is usually kind of like boxed together as UF. Okay. Okay, so this is just a convention. This is what we mean by an oracle. This is what we mean by a black box. And so the idea basically in all of these algorithms is, at least the algorithm that we're gonna learn last time and this week, are these algorithms are to learn something about the function. Okay. All right. So the reason I mentioned this is just reminding you what we mean by these things. So now the idea is that, how does phase kickback connect to this? The idea is that we want to imagine that instead of we want to imagine that y is now in our special and so what you now see is that the fact that let me see, just a minute. I don't want to screw this up like I did last time or the time before. Right. So the idea is that y gets mapped to, like, if you just think of it this way, gets mapped to 0 plus f of x, right? So I'm keeping x for right. X at this point, I'm not complicating. I'm not doing the algorithm yet. So x is just some bit string, and so x is the controlled bit. It's not going to get any action yet. There's no kickback there yet. But what you observe is so x is just coming for right. I'm going to keep it on the side to remind you that it's there. So the idea is that if you have a function, I'm going to go through this meticulously so that otherwise, if I have to look at my notes, that means that I've made a mistake there before and I don't want to make it again. Okay. So what you see is that depending on the value of f of x, you will get a right. So if, let's see. Why do I hesitate to write this? So this is the answer. Let me just write the answer down, and then we'll see why I hesitate to write that. Okay. So the point is that if f of x is 1, right? So you can see, yeah, let's do this slowly. I mean, it's probably more obvious to you than it is to me. So if f of x is 0, right, then the outcome is x tensor product 0 minus 1 over root 2. If f of x is 1, then sure enough, the outcome is x. So it's the same story as with a phase kickback, right? 1. I'm just computing what's in the top line there. Minus 1 plus 1, which is 0, paradoxically. Okay, so that's minus 1, x, y. And so what you see is that the formula is basically as I wrote and erased. So what you see is that, the situation that we exploited to, make a, to do this sort of a trick with a C-naught gate being flipped is actually just a general property of this phase kickback, which is basically says that x, 0 minus 1 state gets mapped to minus 1 to the f of x, x 0 minus 1 state. Okay. All right. I spent too much time on this, but this should be sort of clear. So it's just a rule that we're going to follow going forward. Okay. Any questions? Okay. So the Deutsch-Josa algorithm. By the way, I found, I don't know if I should recommend it to you. I'll send a link. You guys can decide. I found a YouTube video of Deutsch explaining the Deutsch algorithm. So it's a little bit, 1980s kind of vibe, but I don't know. I'll send it. I haven't watched it myself. I don't know if it's worth it. So what is the problem? So there are functions which are constant, distinguish constant versus balanced functions. And this is a kind of a jargon, so the idea is that f of x is constant is, is 0 and 1 irrespective of input. That's kind of right. You basically, before you start the problem, you decide, is it going to be 0 or 1, right? And it doesn't matter. It seems like an idiotic sort of function, but these functions exist, especially if you want to prove something. So f of x is 0 and 1. And this is basically half inputs and the other half inputs. You realize that most functions are neither, right? Most functions are neither. So this is not really a particularly useful problem, but as you'll see, so I think once you have the proof, once you understand how the algorithm works, you'll actually be able to see how it would work if the function was neither, and how it exactly, basically once you have errors in the code, then you'll see how it's more or less back to the usual thing of, well, it's fine-tuned. Anyway, so let me give you one aside, which was kind of like important in Qiskit. Aside, and I'll say C Qiskit, because that's one of the Qiskit problems. And the question is, how do you make oracles? How does one code up oracles? So I would say, you know, constant oracles are easy. Right? Because what you're trying to do is you're trying to kind of like impose the same behavior on all inputs. So the easiest oracle is just constant oracle, is just nothing is happening. And then you start thinking, okay, well, maybe I should apply the same transformation. You know, basically I should initialize this thing into some kind of a state so that it sort of comes out to be one. Obviously, you can hang arbitrary number of NOT gates because these two annihilate. That'll also be nothing happening. So you want to create. There are many ways of getting identity, right? So a constant oracle is basically an identity, possibly flipped by -1. So I'm not going to worry about it too much. So I think the more interesting question is balanced oracles. So balanced oracles. Or so easy or harder. And so the example from Qiskit that, you know, again, you should have internalized because it's a very concrete thing, right? The idea is that you have, you know, so this is your Y and this is your X, right? The example there was that, look, you basically just go in and do a bunch of C0 gates. Okay, and you can convince yourself that this is a balanced oracle. Essentially what happens is that for every 0 input, what you want to see is that for every 0 input, like suppose this is 0, right? The way you prove these things, or at least convince, so there's a difference between proof and convincing, and I think you should think back to your elementary sort of math courses, presumably, you know, I don't know, is it Calc 2 where they discuss proof by inductions? Because I always think of Calc 2 as the place where you guys are taught to do proofs. You know, the way to understand all of these algorithms, at least that's what I usually do, unless, you know, things are really too easy or too difficult, is to try to start somewhere, you know, start with 1, 2 channels, 3 channels, and then by induction, you kind of see what the structure is. And the structure is basically is that each of these C0 gates guarantees that whatever the output of the function is, so this is f of x, right? Whatever the output of the function is, if this register is in 0, if you flip it, sorry, if the register is now 1, the output will be flipped. So that means that you guarantee that for every +1, there's a -1 in the output. Like, so if you make a table of all the outputs, right, by having these C0 gates, you essentially guarantee that if one of the bits in the input is changed from 0 to 1, the output also changes. Okay, and that guarantees the balanced nature of it. So you know, starting from this as kind of like your base, you can now go in and hang a bunch of, you know, scrambling gates, NOT gates, to basically just change the, you know, which inputs give you 0, which inputs give you 1. Again, you can look in Qiskit. Now, so problem 1 in that case basically asks, you know, can you make other balanced oracles. And since we're running out of time, I'm not going to run a poll to find out what people have done with it. My guess is that so far every poll has given a 50-50 breakdown between yes and no. So let's assume that there's a bunch of you who haven't done this. So the only hint I can give you, which is basically the general kind of a protocol for doing this, it's not even like that deep. You want to build the other oracles by looking in the same way that C0 operates. You want to take bit strings and you want to convince yourself that there's a symmetry operation where you flip them and the output flips, right? So my hint would be that try using other gates. For example, the CC NOT gate. So the CC NOT gate is basically you flip conditional on two inputs. I think this is called Toffoli gate. I mentioned the guy who invented this gate is still alive. He's at Boston University. It's kind of weird, right? This is like one of the most popular gates, and the person is still kicking. Still pretty young too. Not very active. Anyway. So yeah, so my, I think the general hint I would give you is that, apply this design principle of just having outputs that are, one by one bit flip, kind of like guarantees that the output also flips, then you kind of guaranteed that things will work out. Anyway, let's continue. Right, so the Deutsch problem was, you need to distinguish between constant and balanced function. Okay. Now this is supposed to be a review, so I'm not. Let's see if I can go actually finish it before we're out of time. I think we're going to have to find more time for class. Okay. So the idea is that we do our favorite Hadamard gates, and I'm going to draw them like this. So we start with a n-bit input, +1 for the output. Then we're going to do our sort of shorthand for the oracle. We're going to do it once, right? And then we're going to apply another Hadamard gate on the so you can see that this is sort of an example of a this is going to be a phase kick. All of these are phase kickback sort of things. And now we're going to measure, and we're going to look whether, right, I don't know how to write this using circuits, but basically you're trying to ask whether the same initial register that you fed in, which is all zeros, is observed on the exit. Okay. I think it's good to go through the math, but because we're kind of reviewing, I'm going to assume that some of you went through the math and some of you may need help going through the math. That's more kind of like, okay, are you following from this equation to that equation, which should be done kind of like on a more tutoring personal basis. I'm happy to do that. So you should reach out to me if this is not clear. So instead, let me kind of give you kind of like a more condensed, sophisticated derivation of this, which is kind of like not even a derivation, it's kind of like an observation that this has to work, right? And it's based on the way I did the review of the Hadamard and other things. So recall that this is an identity, okay? So what that means is that if you convince yourself that on some states, this U does not produce any disturbance, then you're done, because you can see that, the Hadamard takes 0 and rotates it. Then if somehow, for some reason, which we'll explain next, U does nothing, then applying Hadamard again will give you back the same state. So that's basically what happens if your function is a constant function. So let's see how that works out. So if f is constant, I'm just going to write the math as is, in shorthand, right? The idea is that then, in fact, let me just, I want to focus on the state here, on this, at this level of operation. So what I want to do, I want to take 0 to the n, I want to hit it with the Hadamard, and I want to hit it with the UF. Okay. Yeah. Okay. This state is UF. Now remember what we said about Hadamard operating on a all zero state is just a superposition of all bit strings X with no phases. It's just all the same phase 0. Now the point is that if the function is constant, what it does is it goes in, well, regardless of what the function is, let me put it this way. This is the general prescription. And if the function is constant, then all of these f of x's are the same. So you all of a sudden, so this follows from the phase kickback discussion that we just had, right? And so if the function is constant, then this is an oral phase plus or minus 1, depending value of the function. And so you get back to the same guy that you had before. So it's the same. And so that means that when you apply the second Hadamard, Hn, on this superposition, you get back 0. Okay. So that's only if the function is constant. Okay. Now, if the function is balanced, all of the same stuff can be written here. Okay. In fact, up to here, right? I'm going to copy this part because it applies regardless. And what you know now is that some of these minus 1 to the f of x are going to be minus 1s, and some of them are going to be plus 1s. So that means that, in fact, I'm going to break them up by hand, right? X pluses is going to be minus x minuses, okay? And this is basically half cases, and this is the other half cases, okay? Now, what can you say about this state? This state is not going to rotate back to 0, 0. But one thing that you know is that this state, let me call this state, I don't know, little b. And I'll call this state little c. So you can see that these two states, b and c, are orthogonal, because you can see that if you try to compute their dot product, you'll have a combination where, you'll have x plus minus x minus dotting with x minus. And so this will be 0 because this is exactly 50-50. Okay. So that means that this state, the b is orthogonal to c. And that means that when Hadamard operates on it, you're guaranteed that whatever the state that you get, I'll write it as final balanced, right? That state will have nothing, right? So if you now expand the state out as sum of various, x's, 0 to the n will not be present. Not be present in that mixture, right? In fact, do we have, no, we're out of time. Poop. Let me just write this in the following way. Well, actually, let me stop here. So I think you should think about this, and we'll continue next time. The idea being that because the Hadamard transformation is a unitary transformation, it rotates orthogonal states to orthogonal states, right? H, I'll just write, is unitary. It rotates orthogonal states to orthogonal states, i.e., you know, B and C being 0 before rotation implies that, you know, the final balance state, as I called it, is orthogonal to the 0. Okay. And so what you see here, let me just make one comment, is that if you now had a function which was not exactly balanced, but had a few outputs that had few more ones versus zeros, then the output will actually have a little bit of 0 in it. And so simply asking whether, you know, after all of the circuit running, you get a 0 to the n or not, some fraction of the time you will get 0 to the n regardless of, you know. Oh, you just, you know, the fraction of the time actually tells you how unbalanced or balanced the function is. Okay. All right. Let me stop and ask what, if anything, people can tell me about, you know, how this is going, whether this is a way, you know, I think for some of you who kind of like are on top of the homeworks, this review was probably too much. But I also know that there are people who are roughly a third of you, or maybe fewer, I haven't checked my email, haven't done the homework or haven't been doing the homework. And that kind of worries me, that they're kind of just generally not following the class, even when they log in. I mean, you should feel free to, you know, give me feedback, you know, by email. Yeah, I think, Aaron, I got your homeworks. Thanks. Yeah, there were people who sent me a bunch of stuff last night after I sent out kind of like wake up calls. Now, look, I understand that this is sometimes things fall through the cracks. So I want to make sure that this is the time where roughly at the half semester sort of a point, this is the time where, you know, big adjustments can be made both on my end and your end. So especially, I think I don't want to shortchange people who are kind of like getting the stuff. So I will kind of like try to do more in class. I think this is partly, you know, me adjusting. Okay, there are people asking me if I got their homeworks. I would have to kind of tally things up. I will send out, now that I've figured out how to look things up, you know, everything else, I'll tally it up. And, you know, if you have any worries about your homework, definitely email me and I will respond to you personally. But I think, you know, my main concern is people who haven't turned in any homeworks, and there were about 4 or 5 of you. I think that's my, or at least I thought so. All right, I need to look up. All right. Let's see. So I don't think I formally made a due date for homework 5. I'll take that as an opportunity to add a couple more problems to make it more interesting, because so far, just please work on Qiskit, get this done. You know, but I think it's, you know, there should be some more challenge to it. So I'll try to do that before tomorrow. Maybe we'll make it due next week. Okay. All right. Any questions? I'm going to hang up then. No. All right. All right. See you guys tomorrow, hopefully. Bye.
Professor, see you tomorrow.
Yep. Bye.